times we can troubleshoot a transistor circuit and figure out what's wrong with it without ever pulling it out. Now we always pull it out and check it with a meter to confirm that. But what measurements will we use to determine if a transistor is saturated or? So what's the three regions we can operate a transistor in? What three regions can we operate the transistor in? No, we're talking about the three regions we can operate the transistor within. And this is all transistors, whether FETs or. We've been dealing exclusively with this. We've been talking about this several times, guys. I don't know what's going on. I mean, so what are the three regions we can operate a transistor in? Okay. I'm going to give it to you one more time, and it's going to be on a lot of tests. We can operate it saturated. Okay, what's the other two now? Saturation, cutoff, or we can operate it in the active region. In saturation, it acts like a closed switch. In cutoff, it acts like an open switch. In active region, it acts like a rheostat. Those are the three regions we can operate. So when I operate it as an amplifier, this is the guy right here. When I operate it as a switch, this is the two guys right here. We operate it in saturation and cutoff. So how can we tell which one of these regions the transistor is operating in? What measurement can I make using my meter to determine what region this transistor is operating in? Of all those different measurements we went over that we used, we had one that we could use to determine what region the transistor is operating in. No, so there's no such thing. I look at this meter, there's no such thing as active on it. So I can use a measurement with this meter. I can measure something with this meter to determine what region this transistor is operating in. You're talking about checking to see if the transistor is good or bad. I'm trying to see whether it's acting like an open switch, whether it's acting like a closed switch, or if it's acting like it's acting like an amplifier. So here's my transistor. Where's the switch at? So if this is the emitter, and this is the collector, and of course this is the base, where is the switch at? Where's the current? Where's the valve at? What valve are we controlling? Where's the valve at? Between what two leads? Between the collector and the emitter. So when I say it's acting, so we got this voltage called VCE, voltage collector to emitter. So VCE is where we can, if we measure VCE, we can determine just like that what region it's operating in. So in cutoff, VCC, voltage collector. So that means I take my meter and I put it right there, and I put it on volts and I measure right there. That would be my voltage collector to emitter. This is what's common. So on those, the one on the right is where you put your black lead at. And on transistors, you really need to do that because to bias the transistor, we have to have certain polarities, right? You understand that? Okay. So what do we do? What would be, what if it's saturated? What would we measure voltage collector to emitter? Yeah. So here we go. I'm gonna draw this up here. So here's my collector resistor, or here's my load RC. Let's say I got 20 volts up here, and I've got a switch down here. And here's common right there. Here's my emitter. Here's my collector. And the switch is open. If I measure across that switch right now, what would it measure? If it's open, what would it measure? Okay, so I got 20 volts up here. I got common right here. How much voltage is RC dropping? It's going to measure 20 volts. That's exactly right. So what is that? Is that open, or is that saturated or cut off? So if cut off, VCE is going to equal to VCC, the collector voltage. Okay, so let's close the switch. Now what would my meter measure? So if I come over here, so basically what I'm doing, guys, and this is something very, very important too, and I put my meter on volts, and I come up here and touch the two leads together, that's what I'm doing. What does my meter measure? So if I measure across a closed switch, it's going to measure what? It should measure what? Because look, that's a straight piece of wire. If that's a straight piece of wire, that's me coming up here doing this, right? You understand? What does my meter measure? So how much voltage does a closed switch drop? 0. Okay, y'all understand that? Of course, our transistor is not a closed switch. We don't say it is a closed switch. We say it acts like one. There is stuff in there that's going to drop a voltage. So here we say if our voltage, if VCE is less than 1 volt, so 1 volt would be bigger, then we consider it to be saturated. So what would be active? If it's between 1 volt and VCC, if it's between 1 volt and VCC, we consider that to be the active region. So what do I use to determine what region the transistor is operating in? I just measure the voltage collector to emitter. So these are the 3 regions. What we're dealing with right now is we're dealing with these 2 regions right here. Pretty soon we're going to deal with this region right here, the active region. So we use transistors as switches all the time. I mean, we use them as switches all the time. We use other devices too. It's hard to use a transistor to switch an AC circuit, but we can definitely use a transistor to switch a DC circuit. So normally when you get into PLCs that's got DC outputs, so this is a PLC output circuit. And it's a saturated switch. If it's a DC output. If it's an AC output, we got to do something else. This is what we call a optical, it's a optical isolator or an optical coupler. And I think we talked about this. This is inside a unit. Usually got 4 pins. And then what we do is we transfer information from the PLC over to this guy through that. So if something happens and you screw up out here, then it's going to blow this photocoupler and it's not going to blow your PLC, right? Does that make sense? What happens is you might lose one of your output ports, but you don't burn up your PLC. And a lot of times what you can do is you can move your output over to another output and just redo your programs. If y'all have had PLC, y'all had PLC? You had no PLC? Now, well, this is actually a DC output. This would be a syncing output. So all they use is saturated switches. That's all they use. And that would be DC output. So we want those things to be either switched between saturation and cutoff. If I come up here and look at an amplifier, though, we're not going to see any switches inside that thing. I might have. No, that's a power supply. So this is a power amp. This is I don't know what this power amp is. 2-channel stereo. But you won't see any saturated. These are not saturated switches. These are all in parallel, by the way. And we'll talk a little bit about that. This gives us the ability to control a lot of power, because what we do is we divide that power over 6 transistors. So if each one of these transistors was handling 20 watts, then that would be 120 watts that was hooked in parallel like that. So if we hook devices in parallel, we can increase the current, right, or reduce the current through one, basically because they're shared. So one of these would be the left channel, one of these would be the right channel. This is the power amp. And even though they're still doing a lot of integration in power amps now, where that front end over there might be integrated into a single package, your power transistors are still separated out. Those guys hooked in parallel. I don't know what I did with that. And I think so here we give you the beta, we give you the cutoff current. So what you say, what's electrical going to be? So if we saturate the transistor, this guy's going to drop all the voltage, this guy's going to drop none, right? You understand? So your saturated collector current, your saturated current is going to be whatever requires this voltage, this resistor right here, to drop 20 volts. Because we assume the transistor is dropping none because it's going to be less than a volt, right? Y'all understand that? So it might be dropping, I think the I don't want to I can open up another version of Blackboard. So this is a TIP 41. It comes in a TO222 package. And this guy here can handle a continuous collector current of 6 amps. They can dissipate. Continuous collector current, continuous current, continuous dissipation. So this side here can handle 65 watts. Voltage collector to emitter saturated. So this guy right here, when it's saturated, it's going to drop a maximum of 1.5 volts. But it can break over. So the TIP 41. Now this is a very, very important rating to know. This is your breakover voltage. Now what this stands for, a lot of data sheets don't put BR for breakover voltage. This stands for collector to emitter with the base open. So if the base is open, the transistor has no base current, so it's cut off. And then, of course, then we start putting voltage across that transistor, and sooner or later, it's going to break over. Y'all understand? Just like a diode will when you reverse bias a diode. So this is the breakover voltage on that collector to emitter. So these three versions, this version could handle up to it could block up to 40 volts. This guy could block up to 60 volts. This right here could block up to 80 volts. And then the TIP 41C could block up to 100 volts. That makes sense? I don't see the other breakover voltages. Normally we get a collector to emitter breakover voltage, and we get a base to emitter breakover voltage. And we also get a base to collector breakover voltage. And here's H of FE. So this guy could have could have a gain anywhere between 15 and 75. Minimum would be 15, maximum would be what? 75. So this guy here is going to drop less than 1.5 volts when it's saturated. And when we saturate it, we can get up to what? 6 amps on this guy. Oh, here's my breakover voltage base to emitter. This is reverse bias because forward bias it's going to drop about 0.7 of a volt. So if I ever put more than 4 volts reverse bias on my base to emitter, the transistor is definitely going to cut off, but then it would break over base to emitter, right? You understand? And that's not good. Anytime you break over a p-n junction and you don't protect it, then you're going to have problems. So the Zener, we protect it with that RS, right? You understand? But a Zener is designed to work in there, but these junctions are not designed to work in breakover. So it's just like a regular p-n junction that's not a Zener. If you break that sucker over, then odds are the transistor or that junction is going to be damaged. So that base to emitter breakover voltage is very small. So we can't put a lot of DC voltage on our base. How about you put in the 3 amps into the base, so that's a pretty good size, pretty good base. But 65 watts. So when I'm operating in cutoff and saturation, we'd be looking at this 6 amps. When I'm operating in active region, we'll be looking at the 65 watts. So active region, we're concerned with exceeding the power rating of the transistor. Cutoff, we're concerned with exceeding the current rating of the transistor. Does all that make sense? So this would be a pretty good transistor. It's got a gain of a minimum gain of 15. The 3904 has a minimum gain of 30. So I could use that minimum gain of 30 and run it into this, and what would be my total gain if I hook this thing in a Darlington arrangement? So what does that Darlington arrangement mean? You're going to run into this a lot too. Because what do we get when we hook up a Darlington arrangement? We got several features of this. So Darlington means I come over here and take the output of one transistor and I feed it directly into the base of the next transistor. And then sometimes we put resistors up here. Sometimes they just come up here and connect them together. And this is called a Darlington arrangement or Darlington pair. So a 3904 has a minimum beta of 30. This here has a minimum beta of 15. So what would be my total beta? Huh? I didn't hear you. 450? How'd you get that? Yeah, you multiply them together because they're gains. So it means I got to give that. Now I would have an overall beta of 450, which means if I put 1 milliamp in, I'd almost get a half amp out, right? Which is pretty good. So what they'll do is, like I said, we can look these up, but they sell these things. And it looks like a transistor because how many leads does it take? It takes 3. It takes 3 leads. So they could put this in a pack with just 3 leads coming out of it, and it looks like a what? It looks like a transistor. But then when you start checking it with your meter, it don't measure 0.7 volts, it measures 1.4 volts, or right around there, you say, well, this sucker's bad. Yeah, and you can't look at this junction right here. So if I check between here and here, I'd measure 0.7. If I check between here and here, I'd measure 1.4. So it appears like it's bad. And I'd made this same mistake. I was working on a printer, and the schematics, they had the thing drawn like that. That's the way it was drawn in the schematic. And we were having a problem with it right in that section, and I was checking it, and it measured that 1.4. Well, it measured more than that. The meter I was using wouldn't put out over 1 volt. So the only thing the meter I was using at the time, these new meters will usually put out enough to break over an LED. The old meters they didn't put out over 1 volt when you put it on the diode scale, so they wouldn't break over 2 junctions. So what was happening is I had a good junction up here, and then this junction checked bad, it checked overload. So what did I do? I changed it out, and the printer did the same thing. Well, then I got smart and I looked up the part number and found out it was actually a Darlington transistor. And then everything made sense. But what I was going by the schematics. And when they drew the schematics, they drew it as a single transistor. So don't take for granted schematics are always correct. So I could do this, and so Darlington is a very popular way of hooking transistors because we get a real high beta. I mean, real high, because the betas are what? They multiplied. So, and that's minimum beta. You know, odds are we would use minimum beta when we design the saturated switch, but if we was to operate this thing in the active region, like in a power supply, we operate it in the active region, then the beta is going to be somewhere between there, right? That makes sense? Huh?